Okay, so I'll be beginning with a new data structure which is trees. I mean, it's my first time I'm writing trees after linked list. So in linked list, it was circular linked list, doubly linked list, and singular linked list. I guess that's the implementation again. Anyways, so trees is the data structure that we have seen so far, such as linked list, stacks, and queues for linear data structures. So again, these are non-linear data structures. And continuous linked list, each node has a link which points to another node in a tree structure. Each node will point to several other nodes, which may then point to several other nodes. Okay, so this is how things work. There are other nodes which point to several other nodes. Thus, a tree is a very flexible and powerful data structure that can be used for a wide variety of applications. For example, suppose we wish to use a data structure representing a person and all of his own descendants. Rahul that he has three children, Sanjay, Samir. Also suppose that Samir has three children, Abhay, Ajit, Madhu, Nisha, and Kalne. Descendants squad in the tree structure. Okay, so Rahul first thing points to Sanjay, and then Samir, and then Nisha, and then this thing points to another thing, and it's basically a family tree which is implemented using linked list. So as you can see, there are multiple nodes for the address thing. Each tree contains name for data and name for pointers or other three nodes. All the nodes in general tree may contain any number of pointers to the tree nodes, and large number of data structures have the have at most two pointers to the other tree node. This type of tree is called binary tree. Restrict our trees to binary trees only. Okay, so now we'll be referring to binary tree where there are only two pointers. I mean, till now we had three pointers. I mean, this was three pointers. So we go for two pointers than in binary trees. I guess binary tree is what that everything revolves around. Let us begin to study our binary trees by discussing some basic concepts. Where did that go? Okay, by discussing some basic concepts of the simple binary tree. So this is a simple binary tree. A, B, C, D, E, F, G, H, I. A binary tree is a finite set of elements that is either empty or is partitioned into three different subsets. Okay. Finite set of that is either empty or partitioned into three different. First subset contains a root of the tree. Other two subsets are themselves binary trees. Call the right and right subtrees of original tree. Okay, so A is the root here, and this is the left, and this is the right subtree of the tree. Each element of a binary tree is called a node of the tree. And yeah, tree consists of nine nodes with the left subtrees. Okay, where did that go again? Yeah, like tree each binary node of the tree and tree consists of node. The left subtree is rooted at B, and then right subtree are indicated by two branches, estimating A to B on the left and C on the right. Absence of branch indicates an empty subtree. Fine. For example, the left subtree of binary tree at rooted C. Okay, it's an empty, so left thing is not rooted, and whereas the right thing is C, and the right subtree is binary rooted at E. So that is called an empty subtree. Noted at E both empty in binary trees rooted at D, G, H, I. D, G, H, I have empty left and right. So these are called as leaf nodes. I mean, the last ones are called as leaves. They're similar to the tree where we have a branch and then node. And I mean, the leaf figure illustrates that data some structures are non-binary trees. We show that you understand why each of them one binary tree is just defined. Okay, so if you look closely, this is not a binary tree and this is not a binary tree. How? So this thing has the two pointers. I mean, this cannot be a pointer to this thing as well. And here sharing happens is also not possible. I mean, two nodes are pointing to the same same leaf or node, whatever. And here is the same case again. Two nodes are pointing to the same one. I mean, two nodes are pointing, but I mean it should point to two nodes, but two nodes should not point to it. So here it's what happening. Two nodes are pointing to the node. A node should split to two. I mean two separate nodes, but two separate nodes should not be pointing at a single leaf or branch. Let us now get used to some more terminology in association. Okay, if A is the root of binary tree and B is the root of its left or right subtree, then A is said to be father of B and B is said to be left or right son of A. A node has no son such as D, G, H, or I. Okay, D, G, H, I. A node that has no sense such as D, G, H, I. Okay. Of figure 5.13 is called a leap year. It was what I was saying. In general, any node say N1 is an ancestor of N2 and N2 is a descendant of N1. If N1 is either the father of N2 or N2 is the father of some, for example, tree of figure 1.3, A is ancestor of C. A node N2 is the left descendant of node N1. If N2 is other lessons, A is right descendant meaning like two nodes are together if they are left right. Oh, I missed up the. It's a family relation again there. I didn't understand anything. I just need to repeat reading it again. So in general, any node say N1 is an ancestor of node N2. So A is ancestor of B, ancestor of N2 is a descendant of N1. If N1 is either the father of N2 or the father of some ancestor of N2. Okay, so let's say F. So A is father of C when C is father of F. So F is ancestor of C. So A is an ancestor of C. A node N2 is a left descendant of node N1 if N2 is either the left son of N1. So let's say H is the left descendant of node F. If H is either the left son of F or a descendant of left son of F. Okay. So here D is also covered into the left descendant of node N1. So I guess right descendant will be similar different. Two nodes are brother if they are left and right sons of the same father. So H and J are brother nodes and they are not of the same I mean the sons of the same father. Although natural trees grow with their roots in the ground and their leaves in the air. Natural trees grow with the roots in the ground and the leaves in the air. Computer science is almost universally quoted trees with the root at the top and the leaves at the bottom. Direction of the roots and leaves are down and opposite direction. So the direction from the root to the leaves is down and opposite direction is up. Going from the leaves to the root is called climbing the tree and going from root to the leaves is called descending. So again, I mean this book has explained properly how things are and how terminologies are. So he's just saying simply that going from the leaves to the root is called climbing the tree. So I'm going from G to A, it's climbing the tree, and I'm coming from A to G, it's again descending the tree. If every non-leaf node in a binary tree has a non-empty left and right subtree, the tree is terminated as if every non-leaf node, okay, what is non-leaf node, has a non-empty left and right subtree, then the tree is termed as strictly binary tree. Thus, the tree of a figure 5.15 is 60 because everything has a right as well as binary left node actually. D has a left and right, and this is also left and right, and this also has a left and right. So every non-leaf node in a binary tree, so it's a non. This is a leaf node. We will not consider this, but this is a non-leaf node. It has a non-empty left and right subtree, so it's a strictly binary tree. Whereas that of figure 5.13 is not a strictly binary tree. Why is it not? Because E doesn't have a right node and C doesn't have a left node. Level of node is the root of the tree has level 0. Level of any other is 1 level. For example, in the binary tree. Okay, this is somewhat coding part. Level of node in binary tree is follows. Okay. The root of the tree has level 0. So this is the root of the tree, it has level 0. And level of any other node in the tree is 1 more than level of its father. So this has level 1, we see, because it has level 1 more than its father. For example, in the binary tree of figure 5.13, okay, node E is at level 2, level 0, level 1, level 2. And then node H is at level 3, okay. Depth of binary tree is the maximum level of any leaf in the tree, okay. This equals to length of longest path from the root to any leaf. Thus, the depth of the tree of fire is 3. A complete binary tree of depth 3 is a 60 binary tree of following method. Wait. A complete binary tree of depth D is a strictly binary tree of all of whose leaves are at level D. Okay, let's try to understand with the help of this figure. 5.15. So a complete binary tree of depth D. What is the depth? 0, 1, 2, 3. Depth 3 is a strictly binary tree of all whose leaves are at level D. Of all of whose leaves are at level D. Okay. Complete binary tree. Okay, there's the again definition of complete binary tree. Okay, this is the complete binary tree now. Level 0, level 1, level 2. Depth 2 is a strictly binary tree. All whose leaves are all at level D. Of the depth D, all leaves are at level D. Okay, so this is the complete binary tree and it's a strictly binary tree. There's a difference between both. So a complete binary tree is the tree which has both where I mean there is no root node having only left or only. I mean every node has a left or right. A, B, C, D, E, F, and G. So this is the hmm, strictly binary tree. So we can come to a conclusion that complete binarity is also a strictly binarity, yes. Because A, then B, and then C, then D, E, F, G. Okay. Then comes the traversal of binary tree. The traversal of binary tree is to visit each node in the tree exactly once. Binary traversal is useful in many applications. So it's like traversing a linked list where we visit the linked list each node every time. Okay. And useful in many applications. The order in which nodes of linear list are visited is clearly from the first law. However, there is no such linear order for which the nodes of the tree. The methods differ primarily in the order in which they visit the node. There are three popular methods of binary tree traversal, known as in-order traversal, pre-order traversal, post-order traversal. Oh, I mean, these are no heavy terminologies which I'm coming across. In each of these methods, nothing need to be done to traverse an empty binary tree. In each of these methods, nothing need to be done to traverse. Okay, that is quite trivial thing. A function used to traverse a tree using these methods can be kept quite short if you understand the recursive nature of this binary tree. Okay, so this is where recursion comes into play. We call that binary tree is recursive in that each subtree is really a binary tree. Binary tree is recursive in that each subtree is really a binary tree itself. Okay, so this is a recursive because this is a binary tree itself. This is a binary tree. Wait, let me. Traversing involves visiting the root node and traversing its left and right subtrees. The only difference among methods is the order in which the three operations are performed. Okay. To traverse a non-empty binary tree in pre-order, we perform the following three operations. So this is the root here. Insert the root, traverse the left subtree in pre-order. Oh, now what is meant by pre-order? In order, pre-order. No, I need to pull it up. There's an order before it is available for purchase. Order for product before it is available for purchase. So I think the assignment comes from the same thing. Data structures. Okay, the assignment is there. And okay, and this is the heap implementation. Okay, fine. Pre-order will perform the following three operations. In pre-order, now we are performing the pre-order traversal. Visit the route. This is the route. Traverse the left subtree in pre-order. Traverse the right subtree in pre-order. In order or symmetric order. Traverse the left subtree in order. Visit the route. Traverse the right subtree in order. Okay. Traverse a non-empty binary tree in post order. Now let's just understand what is this post order. Many algorithms that use binary trees proceed in two phases. The first phase builds a binary tree and second traverses the tree. As an example of such an algorithm, consider the following sorting method. Given a list of numbers in an import file, we wish to print them in ascending order. As we get the numbers, they can be inserted in binary tree such that one of the figure 5.17, when the number is compared with the contents of a node in the tree, a left branch is taken. Wait. Okay, so as soon as numbers are there, they're being transferred into the binary tree. Okay, that's fine. Clear till there, and then the number is taken in node tree. A left branch is taken when number is compared with the contents of node tree. Okay, a left branch is taken if the number is smaller than contents of the node, and the right branch if it is greater than or equal to contents of it. So if the input list is, I didn't get what it is. New algorithm proceeding to present the number they can mention and the figure frequency. When a number is compared with the contents of node in the tree, a left branch is taken if the number is smaller than contents of the node. Okay, so 12 is smaller than content of node, so left is taken, and right branch if it is greater than equal to contents. Thus, the input list is this thing. Binary tree of this thing. Such a binary tree proposes that all elements in the left subtree of a node n. So all the elements in the left subtree of n are less than the concept contents of n. Yes, that's fine. And okay, how did you insert it first of all? 2017. I mean, how where did you decide to split? Okay, I got it. I mean, what is the method of creating the tree? How is it done? Is a number well, okay, a left branch is taken if number is smaller than contents of the node, and right branch if it is greater than or equal to contents of node. So 2, 20, now 17 is less than content of node, so left branch has been taken. And then we have 6 and 8. Wait, 6? I think it's 8. Oh, okay. Now 6 is taken because 6 is less than 17. And then 8 is taken on the right side of 6 because there is not it's not possible to create another branch. So 8 is taken on the right side of 6, then 10 is taken on right side of 8, and 7 is taken on left side of 8, and then 10 and then it's 18. 18 is taken on right side of 17. Okay, now it moves further, and then 13 is taken on right side of 10. 12 is taken on left side of 13 and 5 is taken on left side of 6. Okay, let's see how is it being done. Such a binary property that run the doesn't contains of n and all elements of right angles are equal to constants of n. Binary tree that has the property is called binary search tree. Okay, BST. Binary search tree is traversed in an in order left, right, and the contents of each node printed and not represented. The numbers are printed in ascending order. Okay, convince yourself that this case for the binary search tree of figure 5.17. The program to implement this algorithm is this thing binary tree. Damn, I- the code is quite large. The code is really too big. Okay, no problem. Threaded binary tree is this is support again. It's again. Oh, these are graphs. Fine, trees, graphs, and then I mean these are the things which makes DSA look DSA, data structures and algorithms. These are the quite. I mean, these are only they add up spice to the concept. And there are several algorithms like DJ class, this class. I don't know how to spell that. 26, 7, 8, 10, 17, 18, 13, 12, 5. Let's see how is this being implemented. So 20, we move with the next element 17. I'm doing it on a pen and paper. 17 is less than 20, it will move here. And then move with 6. 6 is less than 17, it will be on this side. I mean, we just do it again from this side. 20, 17, 6, 8. Where will 8 go? 8 goes on the right side of 6. And then we have 10. 10 goes on again right side of 8. And then 7. 7 goes on left side of 8. And then 18. 18 goes on right side of 17. Or else it goes on right side of 8. Then why is it not being considered on the right side of 10? Okay, okay. As soon as we encounter larger limits, we just start pushing to the right or what? Right? Right. Okay, let's say 18 to 17 goes to 18 goes to 17, then 13. What it is saying is when a number is compared with contents of node of a tree, a left branch is taken if number is smaller than contents of the node, and right branch if it is greater than equal to contents of node. Okay. No, 7 over here, now it's 10, and then we have to go to 13. 13 goes on right side of 10, and then 12 goes on left side of 30, and then 5 goes on left side of 6. Okay, 5 goes 13. Okay. Hmm. It's a binary trees property that, okay, elements are node of subtree less than equal to property that elements in the left subtree of a node are less than the contents of n. So elements of the left subtrees are whatever all are less than 20, and then elements of right subtree of n are greater than equal to contents of n. So whatever the elements are in the right subtree, they're all greater than equal to the elements of whatever in the present in n. Okay. Binary search that has these properties is called binary search tree. In order, if a binary search tree is traversed in order, left, okay, first is left, root, right. Are we climbing or descending the tree? Climbing the tree is going from root to branch. So left, root, right, then no. I mean, it's going from descending the tree, I guess. In order is okay. Then the numbers are pretending. Convince yourself that this is the case for final efficiency 5.17. Then the program to implement this algorithm is as below. Instruct binary tree node left child, right child, bt I is equal to 1 num. Okay. Enter the data, insert bt num in order traversal, p order traversal. Insert the new num into binary tree. This is the node and this is the in order traversal and this is the reorder traversal and this is the post order traversal. Okay. And this is the deletion from the binary tree. But before deletion and after deletion of node I. Okay, so after deletion of node I, L has been placed instead of it. Or simply just deleting the next list nodes, I guess. Okay, let's try doing coding with L. I think after doing this one, I might be able to solve the 1400 related questions on code forces. Most probably. Okay, let me just so I'll be more, just doing with the Vim editor. Touch bst.c with bst.c. Okay, so insert code. What else to include? Log.h is nothing but being it's been deprecated, I guess, and it's just a std let. Okay, let's just see how things are being done. Implement a binary tree struct binary tree node. Binary tree node when they have later left child, data, and right child. Okay, this is what was the definition of our binary tree node. And now we have binary tree node bt requires I equals to 1 now. So bt is equal to null. Initially, um, it's been initialized as a null entity and then specify the number of data items to be inserted, scanf ampersand requirement to the data and then insert into binary tree. And these are all traversal method. Now let's see how insert works. So insert struct binary tree node sr int num. If the binary tree is an empty tree, then what I'll do is I'll initialize it. Left child will point to the null pointer, right child will point to the null pointer, and data considers none. Okay, fine. Or else, if it's not an entity, search node will to which new node will be attached. If new data is less, traverse to left. If num less than sr data, insert ampersand sr left child fine, else traverse to right. Okay, uh, it's too awesome actually. I mean, just 2 lines here, I've completed the code. If this was possible to understand, if you tried doing linked list from this book, especially understanding pointers in C. And now this is the traverse in binary left data right fashion. Okay, this is called as in order traversal. And what has been done is if SR not equal to null. What is SR? That is, I mean, on what basis did he rename it as, name it as SR? SR not equal to none in order SR left child. Okay, this is a base recursive function. Print SR data in order to means written. So they all go till null and first we print the left child and then it prints the data. So basically we have a binary tree like this thing. So we go with the left child, then it prints the node data, and then it goes with the right child. And then left child it enters here, and then it prints the left child, and it goes with the root data, and then prints the right child. And yeah, it goes on vice versa. And then print, where is this flash is being printed here? Star data, and then, okay. Okay, let's try till this thing. I mean, we'll try post product this thing. So it is basically inserting, inserting elements in a. So it's known as a binary search tree, if I'm not wrong. What thing made it to be known as binary search tree? In order traversal, post order traversal. Okay, binary tree that has these properties. So the properties being exhibited by the system makes them called as binary search tree. Now what I'll be creating is a function. First of all, let me initialize the structure. Let us use the naming convention as we have used it. Struct B tree node. Now what does the struct B tree node have? It is Vim supported in Windows as well. Okay, anyways, now struct binary tree node. What I'll be doing is inserting elements. What are the elements to be involved? So it will have a struct left B tree node left child, which is a pointer actually, which stores the address, and then we have the integer data which I will be storing, and then there is a binary tree node right child. Okay, I think this is what it is. Yeah, and data. Okay, right child, left child. Okay, now we'll move the main function. Now, what do we have in the main function? Let's see. I think now there is no restriction to solve much problems on code forces after learning this thing. I think I will be able to solve till 1500 difficulty after learning this. Okay, now it's the main function. And main function is struct b3 node sr is the whatever binary search tree, or else what is being named as bt. And then so int n, and then or else int required, and then yeah, printf and the number of elements. And scanner percent b and percent whatever requirements I'm needing. And now for and equals to 0, I just get requirement. I keep on implementing. Now what will I do is yeah, int x and taking this input scan percent b percent x, and I'll just insert it. I need to define the name same as thing. So it's just defined as insert. insert ampersand bt. Okay, okay, fine. Then now I want to go with the traversal method. Pre-order or post-order. What does it mean? Order? Okay, first one is in order traversal. In order, struct. Okay, and stop copying bt node and st. No wait, that's a function initialization. What I need to pass is bt. I think this prints in order traversal. I think the assignment question also consists the same. Given another traversal binary consists of binary tree. Okay, in order and post order traversal are given to us. And construct a binary tree, traverse and print the nodes in post order traverse. Input test this one, pre-order in order to traverse. Not is the output of this thing. It's not mentioned. Okay, I need to construct a binary tree in the pre-order. So in order is basically LDR, left node data right node, and the left node data right node, left node data. And this is RDL or I'm not sure. Fine, we'll come to this later. Prints in order traverse. Now I need to define the function. What is the function which I will be defining is insert. Insert struct b node and sr and int now. Okay. Now what I'll be doing is I'm inserting values. How can this be happening now? Now first of all, sr is int temp. If sr is equal to null. If the tree is binary is initially empty, then what I'll be doing is sr is equal to malloc struct malloc size of. I think I need to learn Vim. But it's actually a cool thing. I mean, it looks so cool to type the code with your hands and everything without that VS Code thing debugging you and finding your faults and irritating you. It looks really good to write on Vim. Okay, this is how it's done. And then, and then it doesn't matter what thing what they're assigned now. And how do I put on start? I think there would be a step function. And the left child is point on pointer, and then right child is again up the pointer. Okay, and then just return it. Now, else if that's not the case, then what I need to do is s how will I insert now? No, that's the point. If the required data is less than root node, then insert the data in the left, whatever, left side. Else insert it into the data of right side. Okay. Okay, fine. I don't know how to compile in Vmaster, how to compile a C file because I had a make file which used to do the task. I mean, I need to do the make file thing way now. Okay, I'll just look after that later. Okay, if num is less than SR a data, then if num is less than this thing, it's just simple two line of code actually. Then insert person SR. This goes to left, left I believe. That means less it goes to left. If it is greater, it goes to the right. Yeah. If it's less, it goes to left child, and then I need to pass the address of this thing as well. But if you are working with pointers, it's really good to use VS Code because it just gives you error right there where we compare invalid pointer types or pass the invalid pointer arguments to the function. And then whatever data I need to be inserted. Now, else, insert. Okay, then go the right side. And this is what is being done here. And then return as usual. Okay, this is where insertion is being done. Now we move to the in order. What is the return type of in order? Okay, that's normal thing. Order traverse. Okay, let's just see how we made that. How is the order traversal is being done? So first we go to the left, data, and then root. So is the function declared? Okay, it's not declared. In order, struct, bt node, bt. Okay, now in order traversal, I think there's a temp pointer as well. Pass. Okay. Else return up. Some bit of sneak peek. If it is not on the pointer, oh, then I just go for an order traversal of S. Uh, SR and then I will message you for the picture. No, I will use a printf statement and then when the person B, and then else return null. Okay, this is where recursion comes into play. Now I'm done with everything. In order refers LDR fashion. Okay, left data right fashion, and then post out etc etc. I just need to do spacing. Okay, now I define how to compile and how to okay. Where do I need to type this? Exclamation GCC file name dot c or exclamation GCC. What is the file name? What the file name? BST GCC BST dot c and then exclamation GCC BST dot no there's no slash BST dot c o okay. Return type defaults to int. Okay. Okay, I didn't declare the data type. It's a void. Okay, what's that again? Defaults to int. Line 10. Okay, okay. Again, it's of a void function. DCC BST dot c. Oh, oh no, what happened to scanner? Um, the return. Hmm. I think there's no other option than making the make file. I have already set the make file actually. What I just need to do is copy paste this thing. Okay. Now I need to open this in the terminal. and after opening, this in terminal. Now I need to make one file. Okay, fine. After expression, is it the correct file which I'm running? It's not DALC, sorry. It's a different file actually. It's BST. Number of elements. Okay, let's try with the sample given in the this book of Wise. I don't know this name. Number of elements are 1, 2, 3, 6, 9, 10. 10, and that's 20, 17, 6, 8, 10, 7, 18, 13, 12. Right. Okay. In order to travel certain CD assignment, Vim, ESP not C. Okay. Where is the error being produced? Let's check actually. Comparing the code. So the declaration of left child, right child is fine. And then malloc data is none, left child none, right child none. And return non less than SR data. The time percent SR left child none. Okay. I think there's a bracket error with this thing. And then in order, struct BT node SR, not SR, printf DSR left child. Okay, okay. It's written. Yeah, well, I think there's no ampersand X. I didn't forget that. I think error is being caused here. Oh, no. Again, it's a segmentation fault. Now, this time, if it doesn't work, I need to go for ChatGPT. Struct BT node. Size of struct BT node. Okay. And where's the node function? Oh. I don't know what are those nodes. Hmm. I guess there's a error in the else statement. It gave some output, but after that, again, I mean, here I achieved the. Okay, okay. No, there's no other option then. The debugging is harder than Vim actually. You need to read everything. It just makes your life more difficult. Oh, fine, no problem. Insert ampersand dt, then another dt. Okay, I did a mistake that I didn't initialize this binary tree. Oh, fine, finally. Oh, this is the node traversal. Let's verify it actually. But where is it being done? Left, LDR fashion, left, data, right. And now again, right is traversing left, data, right. And this is again going to the left, data, right again. Okay, okay, okay. I think it should be 17 printed first. Let me verify it online. Binary search tree. Hmm. Okay, fine. The correct thing. How is it being constructed? Let's see. 20 is root, 17 left of 20, 6 left of 7, 8 left of 6, 10 right of 8, 7 left of 8. Why not left of 10? We're still on 8, right? Yes. And 18. 18 is on again right of 17. Because it's neither, if you see the insert function, uh, when okay, insert function, if it is less than the data, if it is greater than 70, 18 is greater than data, then I'll insert into the right child comma now. So basically our SR pointer points to 18, 20 itself actually. So 20, 17 is less than this thing. So it just traverses again from top. Now let's say I want to enter 17, so I'll insert to the left. Now again I need to insert 6. Now I'll be going bottom. Okay, it goes to the left, and this goes left to this thing. Now again I need to insert 18. So it was 20 from 17, and then it goes to insert 18. But let's say my next element is 17, and then it's 6. So 20, 17, and then goes to 6. And let's say it's 8. So then I move to 20, and I need to move to the further left, and the further move, and then to move to right. Now if I go to 10, then what I came at 20, 17, 6, then it's again still, it's not, it is now greater than 6, so I need to go right side 8, now it is greater than 8, it goes to 10. And then if I go to 7, after 10, that's 7. So 7 is less than 20, so 17 is less than it goes on left side, and 7 is greater than 6, it goes on the right side, less than 8, it goes on left side. And it's as simple as it is. Yeah. Okay, now we'll move to the traversals. And order is being done. And pre-order and post-order. Pre-order traversal is done in a VLR fashion. Void in order and then void DLR fashion is DLR fashion. What is it? Okay, if I go for iterative in DLR fashion, it is again the pre-order data right. That's it. And then post-order is left, right data, LDR, no, LRD. Okay, so DLR is something pre-order traversal. DLR fashion refers to pre-order traversal, and then DRL or RLD, yeah, RLD. Oh no, sorry, LRD. LRD fashion refers to post-order traversal, and then pre-order traversal LDR. Yeah, no, sorry, in order. And it's easy to understand by those names. What happens in DLR traversal, in order traversal, and pre-order traversal. In pre-order, we first traverse to the data, then left node, then right node. Okay. And in post-order, first we left node, right node, then D node. Okay. We in pre-order we left node, data, right node. Okay. In order is something which is done internally. In order is fine. In pre-order, we basically climb the tree, and in something we descend the tree. Left, right, and D is basically climb, going to the root. It's descending the tree, and this is climbing the tree. Pre-order is climbing the tree. Is it's easier to understand this. And just copy paste the function and change the order. I'm feeling too sleepy too. I don't want to do that. I can just move forward and delete a binary tree. Okay. What is after that? I don't know. Well, let's see it better. Pre-order traversal. Struct with tree node. Star. And again, just copy paste the same stuff. So again, pre-order. Pre-order works in DLR version because I need to go with data. Okay, and then it's post order again, the same thing, but now it is LDR. And this is a post order traversal. Post order traversal is kind of LRD. Okay. Post post order. Auto copy paste the line. This vim editor. Okay. Fine. Print of post order traversal slash uh, post order PT and then render pre-order traversal slash fine. And then the outside folder. Make file make run file equals to ps.c. Where is it? Line 50. Okay. Well, CDS time. Yes, that's it. 950. Certain number. 950. Okay. Why was this needed anyway? CD. Uh, 10 elements. What are those elements? 20, 17, 6, 8, 10, 7, 18, 13, 2, 5. Okay. So the post-out traversal, pre-out traversal, and out traversal. Okay. That's it. Now I have to move the deletion. I'll do it later.